So good evening everyone. My name is Antoine. I am the instructor for the course Biostatistics and R, and today we are going to have the class on inferential statistics. We are going to learn more about sampling and estimation. Just quickly I would want to ask that does anyone have any problem with the assignment that you are supposed to submit by tomorrow? I want the mail with every one of the assignment notebooks to be sent to me by tomorrow. The end date is to be sent to me. It is not that you finish by tomorrow night. So yeah, someone please take responsibility. Maybe Dipanjali can and collate all the notebooks in one mail and send me. Does anyone have any problems, any doubts about the assignment itself?
Okay, sir, I'll do the emailing.
Okay, Dipanjali. So we'll be starting today's class. Everyone please turn on their notebooks. Yeah. Okay. So today's class is going to continue with the previous this topic. We are going to study inferential statistics. Today we are going to delve a bit more deeper into sampling and estimation. If you guys remember, we did do a bit of, we have an idea of what sampling is, but we will be looking at it in much more detail now. Okay, let's get started. So if you guys remember that when we are dealing with any data set, then the entire huge big data set is known as the population that we are dealing with. Say we wanted to look at the IQs of all people present in heritage. So that is our population. But as you would know, we can't go about and ask everyone for the data on their IQ. So instead, what we do is that we take samples. We take small parts of the population and look at those and to try and figure out the overall population statistic from that. So one other thing, the population data is known as a parameter, and the sample data is known as the estimate or the statistic of the sample. So we are going to deal with how exactly we can choose a sample and what to do after we get a sample. Okay, so the best kind of sample that you can get is called a random sample. You go ahead and choose people at random, and on the way they are going to the canteen, get hold of them and say, take an IQ test, I am doing a study. So that is known as a random sample, a procedure in which the every member of the population has a same chance of being selected. So it is random, and so that is an unbiased approach. So you will have a better idea of getting every part of the population being represented. Now, if you say you are standing on the door of the canteen and you're asking everyone, like, give me an IQ test, it might be that the same person going in and coming out gives you it twice because you're asking everyone, you don't remember which person you talked to. Then what you're doing is that you are asking the same, you're observing the same data. So maybe he has whatever IQ he has, here it is being entered into the data set twice. So that is called being sample with replacement. So you're replacing the particular person back into the population, and you can actually randomly pick him again. So that is called being sampling with replacement. And when you do not sample, you make sure that you have the names of everyone, you make sure that the same person will not come up twice. It is called being sampled without replacement. So there can be during sampling, the most important thing is that you get a good idea of the entirety of the population. But sometimes that gets difficult, and that is when we get into something known as biases. We are biased towards some population that is easier to get hold of, but we are not looking at other sections of the population. So for the example we have taken, can anyone tell me what bias we are going into? Like, you are in the way of the canteen and asking everyone to just give you an IQ data. What do you think the bias that we can walk into in this case?
সবাই নিজের আইকিউ বেশি বলবে।
That is true. Yeah, that is one thing. But আরেকটা like একটা better like obvious thing, যদি সবাই ঠিকও বলে, there is something obviously biased that we are doing, like standing in the door of the canteen and asking everyone to give us the IQ data.
Like redundancy of data, repetition of same person.
Yeah, that is also possible, that we are taking the same person again and again. He is coming up 2 3 times. You are maybe giving out toffees for everyone who is giving you IQ data, so he's like, yes, I will take one of them. That is possible. That is known as oversampling. But we are also doing something wrong in the beginning. We are only looking at people who are going to the canteen. There are people who do have their lunch sitting in their classrooms. They have their tiffin boxes, and maybe they are not going to the canteen, the main one. They are going somewhere else to eat. So you're not getting those people, right? So that is also a form of sampling, which it is called convenience sampling. So this part, so in which it is convenient for you to get hold of a sample, so that part of those bunch of people are overrepresented in the sample. So this is called sampling of convenience or convenience sampling. It also could also be, you have to get this data set, so you have been asking around and only looking at your friends, and you're going around and asking people you know, but you don't know everyone. And maybe the people you know are very smart people, and you are oversampling from that particular group of higher IQs. So it is known as convenience sampling, in which the samples are chosen in a way that it is convenient for the researcher and not randomly selected. So you would understand that this is also a sort of bias, which makes it very difficult for you to get a hold of the entire population parameter. You will get a sample, but that might not represent the population very well. The other kind of sampling is called stratified sampling. Say you could the data set you are looking at could be divided into different subgroups. Say we are dividing it by the department: biotechnology, computer science, mechanical, civil, everything. And when you start taking the IQ results, you are going around and asking people that you know in the departments that you know. Like biotechnology people never see eye to eye with the computer science, if you know. So maybe you're not taking that many data sets from the computer science people. Most of your data is only from the biotechnology department because you know everyone there. So it is called stratified sampling, because you are looking at a small strata of people or a subdivision of people and taking the data only from them. It could also be the other way around. Say you are looking at a difficult data set. You want to figure out the IQ between people who are mentally ill and normal and healthy. You understand that the population of mentally ill people, you will have difficulties in finding them and finding a larger population of them to match your normal healthy group. But if you want to compare, you need more or less the same number of samples with the same standard deviations. So what you can do is that you can go ahead and just look for institutions where you can actually get this data from people who are not well mentally. And that is known as that is also a part of stratified sampling, which is known as oversampling, in which you go around and you prefer taking samples from a particular small data set or a small group of people, and you do it multiple times, so you oversample a small rare group so that you can get it. And the final kind of sampling is called snowball sampling, in which this one is also not very difficult to understand. It is the case in which you go ahead, ask your friends to give you the IQ result, and then ask them that, you tell everyone you know that I'm doing this, and send them to me. So you ask a first set of people to give you the data. This first set of people knows a second set of people who will then give you the data, and you continue. So essentially you are increasing the sample size, but they are all connected because they are friends of each other. So all of this is known as the snowball sampling, in which you essentially start at a small point and reach more and more of the population, because everyone knows everyone somehow the other way. So maybe you don't know someone from a different department or maybe a different college, but he is a friend of a friend of a friend. So you snowballing can effectively give you the information about a larger sample group, even though you don't know everyone, so it is easier to get. But this can also be biased, that maybe all the friends have higher IQs compared to each other, like smarter people hang out with smarter people, and so even with snowball sampling, you get a higher IQ data set than the population. Absolutely possible. So always, the idea is that you should get a random sample, as like you should always vie for a random sampling and not get stuck with a particular small population or oversampling a simple data set. The why is sampling wrong? Because why is bias is wrong? So what does matter if I ask my friends to give me the IQ data? It is because bias in the sampling method is only problem if you draw the wrong conclusions. Maybe you are friends with everyone in the entire college, so you can actually, just asking your friends, you are still representing all the population of the college, and you can go ahead and ask everyone around, and you actually draw a sample which is random and which is from every part of the population. Just it is still a sample of convenience, but you are not wrong. So it is only wrong if you get wrong results, is essentially what I'm trying to say. Okay, so we'll start doing some R coding. So let us first make a IQ, what do you call it? Let us start by making a data set in which there are 100 people who have an IQ mean of 100 and a standard deviation of 15. So this is essentially what the actual IQ distribution looks like for the entire population, where the mean is 100 and the SD is 15, and we are trying to simulate that population. So if you remember, we did it last time. If you want to simulate or make a random set of numbers which are all from a normal distribution, then you can use this function called rnorm, and you do it for 100 people for mean of 100 and a SD of 15. So if you go ahead and do this, what do you get? So just one thing, that you have to do you have to round up the IQ, because IQs are always whole numbers, they are not decimals, so you have to do that. But I don't think that matters a lot, because you would still get uh, yeah, you do get decimal points. Okay, so if you just go ahead and run it, you should get a distribution which is very similar to this. Everyone please do it.
Done, sir.
Okay, so we get a huge vector of 100 different samples, which are essentially equivalent to random sampling. So if we plot it, you will see, if you just plot it, we have used this function before as well, which is called histogram of IQ, which shows a normalish looking distribution, but yours might look different. Does anyone's look different than this?
So slightly.
Yeah, see, if I run it with the new data, it doesn't look like the normal distribution. The major reason, because the major reason of this is that because your sample size is small. the entire, just the 100 samples cannot effectively simulate the entire IQ distribution of the entire population, and that which is originally normal, but you get a not normalish looking distribution on the face of it. So if I want to test if this is a normal distribution or not, what should I do? If I wanted to test if IQ is normal or not, what can I do? What test I can use?
Sir, could you repeat?
So if I wanted to know if IQ is normal or not, this vector, the data is normal or not, what can I do? There was a particular test that we had used previously, which we used to figure this out. What was the test? Does anyone remember?
So Shapiro test.
Yes, absolutely. Shapiro test, IQ, as easy as that, and we can calculate it. And if the p-value is not significant, then it is a normal data set. So it is normal, but it does not look normal. That's okay. Okay, so if we then go ahead and find the mean and SD of this data set, you guys can try for yours and see what you get. You will probably see that both the mean and the standard deviation look very close to the mean 100 and the standard deviation 15 of the population, but it actually is not exactly the number. This is because your sample size cannot effectively simulate the population statistic parameter. You get close, but not close enough. So how do we fix that? We fix that by doing something called repeated sampling. A small sample of the entire population cannot obviously simulate the data right off. You can't like imagine like 10,000 people and you are just looking at 100 and saying yes, whatever I get from a sample of 100 is my population parameter. The entire idea of sampling is that you somehow get close to the population parameter, but you can't obviously do it with one round of sampling. So what you do is that you keep on collecting more and more samples. You take more and more data from a larger group of people. You hold like one, you stand on the door of the canteen every day for the entire week. You what do you call it? You ask IQ test data from everyone and do it multiple days so that you can get more and more data out of people. So say you did all of that and you did were able to sample from 10,000 people. In this scenario, the population is obviously very, very large. So imagine that the population is infinite and you are able to sample 10,000 people out of it. So you do that, you get a separate IQ data set, and now when you calculate the mean and SD, if you do it for 10,000 people instead of just 100, because you have been asking, your sample size has increased, then you find that the mean and SD is still closer to the population parameter, but not exactly that. You guys should try this out. Just run this 2 lines of code and you will see that you get close to the parameter, population parameter, but not exactly.
So for Shapiro test, the sample size it says must be between 3 and 5,000.
Yes, sir.
For Shapiro test,
It must be 5,000 or less.
yeah, hi, yeah. For Shapiro test, you have to do it for 5,000 at least. I am saying that just run the mean and SD and see if the data is close to the parameter, more closer than the original 100 data set. So this is a 10,000 big data set, and just look at it and see if it is closer.
So not exactly like you got 99.98 for 100 samples only,
Yeah.
I got 99.97 for 10,000.
Yes, you will not get the exact value, but you see that it is moving a bit closer, but not getting the exact is what I am trying to tell
Yes,
you.
sir.
Okay. Okay. So yeah, and then you plot it. It actually looks very similar to a normal distribution now. So that is nice. So we are with larger and larger data sets, we can go closer to the normal distribution. So even just looking at the histogram, if you don't want to look at the mean and the SD, you still know that this larger data set is a better estimation or approximation of our original population, which is obviously normal in shape. We know that it is a bell curve. So our 10,000 big data set is pretty similar to what it should be. So this is known as the law of large numbers, which states that the larger the sample size gets, the closer it approaches the true population mean. So law of large numbers, you ask for more and more data from more and more people, you get closer and closer to the population parameter. Very good. But there is a question: how big of the sample will you get, and is it possible to always get a large number of observations practically? So can you just set out and say, like, I will uh, like in our college, say a large sample would probably be for 1,000 people, or will you just set out, yes, I will sample 1,000 people and not stop before that, and then figure out my parameter from there? So it is obviously not very practical, possible obviously, but not very practical. And there we shift to a different sort of a strategy. Is everyone okay with this far?
Yes, sir, okay.
Okay. So next we are going to learn about the central limit theorem. I will tell you what it is in a bit, but let us start our entire exercise with just looking at 5 people at a time, which is very easy, practically very convenient. So if you just do the same thing that we did, but this time you round it off and start with a population of only 5, or a sample of only 5, and run it, you will see that the data looks, you have a data set. It is a bit higher than the mean would obviously be a bit higher than 100, but you get 5 random samples where you can test the IQ. If you figure out the mean and the SD, they are obviously not at all close to the population parameter. You guys can go ahead and try this out. So it is pretty less accurate than our previous experiments, even comparing to the sample where we had 100 people. This is obviously not at all very correct, and obviously not even close to the 10,000 samples, which are very close to the population parameter. But let us say we do it again. We go ahead and sample 5 more people. We get another data set. We continue to do it a lot of times. So you just go ahead and sample 5 people randomly and start calculating their IQ and then the mean and SD of those groups of 5. if you do this, then you guys can go ahead and just copy paste this command, and IQ 1 2 3 4 5 6 7 9 10. Go and do it. Go ahead and do it. Done.
Sir, run code.
Yeah, run code now, and you will just get it stored. You're not printing it, you just get stored. Like store it into this
Huh,
10. Okay?
got it.
Yeah. Everyone else, please do it. We will do something cool with this. So what have we done? We have taken groups of 5 and we have looked at 10 such groups. So you have essentially taken a look at 50 people, but in groups of 5. Now, what we do is that we figure out the mean IQ of all the 10 groups. So each group has 5 people, 5 IQs. You take mean of each one of those groups, and then you store it in a vector called mean dist, which is known as the sampling distribution of the mean. So all of these are means of different samples, and you make a distribution out of it. So the name follows. It is called the sampling distribution of the mean. This is important because this actually will give us a good idea going forward about the central limit theorem. So you just write down this code. You essentially, what you're doing is that you find the mean of all the 10 samples and you store it into a vector and then display the vector. So you should see something like this.
Sir, can you scroll up a bit?
Yes, I can. This is the code. You just go ahead and
Yes,
type it in.
it's fine. It's fine. Thank you.
Sir, yes, sir.
Yes, Jay. Does it look like odd like this? Like it is not even close to the mean
হ্যাঁ হ্যাঁ হ্যাঁ
distribution. Okay.
মানে হ্যাঁ it looks odd but মানে upper limit শুধু 105 পর্যন্ত গেছে
Upper limit is 105. Huh, that's okay. That because this is a random number generation, you obviously are generating different numbers. So that's absolutely fine. If you run it again, your C will, if I just run it again, then you will see the histogram will change again because random number generation. I think everyone is fine with it. Now, So what we so to get an idea, what we are doing is that we are plotting the sampling distribution of the mean. We are not plotting uh, the we are not plotting the IQs of everyone, but we are taking the means of every one of the groups and then plotting just the mean of the entire sampling distribution. How about we do it for a larger number of people? For that, you don't have to go ahead and write down IQ 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. আমরা for loop use করেছি আগে. If you just run a for loop for 10,000, like you go like 10,000 rounds and do the same thing. It does the same thing. It makes random five. It is sampling randomly 5 people in the population 10,000 times, and you make a vector out of it, which is just the mean of the different samples. So here, making a vector out of the mean of all 10,000 sets of 5 samples. You go ahead and do that.
So can you please scroll up a bit?
Scroll up a bit, yes.
Thank you, sir. It's done.
Okay, so here we are doing the thing for 10 things, 10 different sets of 5, and here we are taking our replicate our sample 10,000 times using the for loop. So try this out and see what happens. Initializing vector, what the fuck? You don't need this.
Yes, sir. It's done, and it gave a normal looking a distribution like this.
Yes.
স্যার আমার একটা এরর আসছে
কোথায় এরর দেখাচ্ছে?
স্যার যখন রান করছে বলছে অবজেক্ট মিনস নট ফাউন্ড
Okay, I feel there is a spelling mistake. একবার share your screen and show me.
ইয়েস স্যার
Means are the square bracket between means আর ওটার মধ্যে স্পেস হবে না।
স্যার তাও এররটা আসছে
ঠিক আছে, I feel then the mean equal to 0 line would have been important. Like do it this way, যে যেখানে for loopটার আগে go ahead
হ্যাঁ স্যার
over the for loop, write means and assignment operator 0. Assignment operator is
ইকুয়ালস টু
that
জিরো নাকি আচ্ছা অ্যাসাইনমেন্ট অপারেটর জিরো
run it again. হ্যাঁ
হ্যাঁ এবার আসছে
ঠিক আছে।
স্যার ওটা কেন হচ্ছে না ওটা কি মানে গার্বেজ ভ্যালু নিচ্ছে নাকি
না, I think because you are just calling means করে একটা means with a I, it doesn't know that it is a vector or not, so it is getting confused, which it should not, but sometimes it happens.
ওকে স্যার
Yeah. Yes. I mean, back. Yes, so now we have, you see now, it very interestingly, the histogram of the means, so we are actually now plotting the mean of these 10,000 different values. And the histogram of the mean itself is normal, which seems odd because it is just a distribution of the mean. Why it should be close to a normal distribution? Here we have started with the IQ distribution, which was normal by itself, and somehow ended up just plotting the means and going back to a normal distribution. So this thing, you don't know, this will take a long time to run anywhere. So if I do it for even larger number of samples, so I'm replicating the same thing what we were doing originally, taking samples of just 5 and then calculating the mean and plotting them. We have done it here for 10, which was not normal at all. Then we did it for 10,000, which looks pretty normal. And then finally we are doing it for a very large amount of people, taking samples of 5 from the population and calculating the mean and then plotting the mean. You see, it is exactly looking like the normal distribution. And this is a very unique thing that happens whenever you take a sampling distribution and you take the mean of each of the smaller samples and plot it, it will always tend towards a normal distribution. Whenever you plot any distribution you take, doesn't matter if the original distribution was a normal distribution or not, you will end up with the sampling distribution of the mean as a normal distribution. Is that clear? Did anyone find get confused? So what I'm trying to say is, when you plot the sampling distribution of the mean, which is means of each sample, you get a normal distribution even though the population might not be normal. Does it make sense to everyone? আর বুঝতে অসুবিধা হচ্ছে প্লিজ বলো।
It's fine, sir.
So the central limit theorem states just this: the bigger the sample size, the narrower the sampling distribution gets, and it gets closer and closer to a normal distribution. And now, if you, the interesting thing is that if you take the mean of this standard this sampling distribution of the mean, oh no, I started this chunk away, it will take a year to follow, it will be very close to the population mean. So you took smaller samples, you took a lot of them, made a distribution of the means of the smaller sample, and when you take the mean out of these sampling distribution of the mean, you get very close to the population parameter. That is the entire idea here. And now you also would get a have an idea that the normal distribution ends up being used so often in statistics and is so important because of this reason. Because if you just plot means of any distribution you can find, then it will take a normal distribution curve. So it is very important that we look at the normal distribution. It is very powerful to do stuff. Okay, so we got our mean, which if we plot the sampling distribution of the means and take a mean of that is very close to the population mean. But what about the standard error here, or the the variance in this sample? So we can quantify. So the bigger the sample gets, the narrower the sampling distribution gets. So comparing this huge data set where you see the tails die of around 80 and 120, here the tails are a bit longer. So more and more data you take, the narrower the distribution will get. But how exactly you quantify this narrowness? This is, if you remember, the further away we are from the mean, that is estimated by something called the standard error or standard deviation. So the standard deviation of the sampling distribution is called the standard error. So how far away each of the means are from the mean of the entire sample. And since we are doing it for the distribution of sampling means, we use the acronym SEM, which means standard error of the mean. So the standard deviation of this interesting new distribution that we got, which is known as the sampling distribution of the mean, is called SEM, or standard error of the mean. Okay, so what does all of this tell you? It's the central limit theory or central limit theorem tells you that the mean of the sampling distribution is the same as the mean of the population. So instead of going around and asking the entire infinitely large population to give you their IQ result, you can just repeat the same thing with smaller samples, do it multiple times, draw a distribution from that, and the mean that you will get is the same as the mean of the population. For example, if I do a mean of this distribution of just 50 people, you find it bang on 100. Here we have just sampled 50, and above we have been sampling 100 and 10,000, right? Here we have sampled 100 people where the mean was 99.21. Here we have sampled 10,000 people, which the mean getting closer, but here with just 50 people we get so close to 100. Here if we do that for 50,000 people, yeah, just 2 decimal places off. Yeah, 4 decimal places off. So this tells you that this tells you the first thing, that the mean of the sampling distribution is same as the mean of the population. Second thing is that the standard deviation of the sampling distribution gets smaller and smaller as the sample size increases. And finally, the sampling distribution becomes normal as the sampling size increases. Okay. So central limit theorem just tells you all of these things. It also says that the population distribution, the entire population mean is given by the symbol mu. The standard deviation is given by the symbol sigma. Then the sampling distribution mean, the mean of the distribution of all the means, uh, is also mu, but the standard error of the mean is given by SEM equal to sigma by square root of n. So standard error of mean is not close to the population mean, but is related to it by this equation. So this is just for information, just take it. So far, so we move on. Is everyone okay with the central limit theorem?
Yes, sir, it's fine.
Okay. Next, okay, so we got an interesting result from just plotting the means, and found out that taking smaller samples, doing it multiple times, is a better way of estimating the entire population parameter rather than going around and asking 10,000 people what their IQ is. Next, we want to figure out if we can find more of the population parameters by sampling less and less of the population. So far we have assumed that the population mean is going to be 100, because we know that the IQ distribution looks like that. So IQ distribution, the standard IQ distribution, has a mean of 100 and a standard deviation of 15. But how do we know that the population mean is 100? Who told us that the population mean is 100? We are not going around and asking infinite people for their IQs. We have somewhere come up with this number that the population mean is 100. So how do you find the true population mean where you probably don't have access to the entire population at all? So whenever you try to find out a mean, then most of the time what you're doing is that you are calculating the sample mean, the mean of just the sample you're looking at. This sample could be 10,000 or 1 lakh or 10 lakhs in size, but it is always going to the sample, because you're not sampling the entire population, because by definition the entire population is infinitely big, or bigger than that you can sample from. So what we do is that in order to find the true population mean, we always go and look for the sample mean, and that is why the central limit theorems come so handy, because you can look at smaller sample size and estimate the entire true population mean from that, even though you could never practically find the IQ of the entire population. So essentially, central limit theorem gives us the opportunity to find or estimate the true population mean from the sampling mean distribution. Okay, so that is sorted. What the you now know what the mean of the population is. But what about the standard deviation? How will you estimate the standard deviation? The first thing you can think is that, yeah, our mean of the sampling distribution of the means gave us the population mean. So what about we try the same with the standard deviation? So if you just run this, and so you are following the same idea, that what did you do? You went ahead and in the previous example took the mean of every one of the samples and then plotted a sampling distribution of the mean, and the mean of the sampling distribution of the mean gave you the population mean. So what do you think? So if you have the same idea now, like what I will do is that I will take smaller samples, and for each sample I will find out the standard deviation and try to figure out the standard deviation of the population from this distribution of standard deviations. If you try doing that and you plot the histogram, you will see that it does not even seem even close to normal. So you can try doing this. So here we are trying to make a standard distribution, a standard deviation distribution from smaller and smaller samples, and we are calculating the SD from each of the samples. So you will probably get a histogram which looks something like this. And if following the same logic, finding the mean of this distribution should give something closer to the true population mean. Everyone with me so far?
স্যার একবার কমেন্টে দেখাবেন আমার এরর আসছে আবার।
Hmm.
ও আচ্ছা, না একটা ভুল। না স্যার ঠিক আছে, yes.
So following the same idea, we have made a distribution of the standard deviations, and finding the mean should give us a mean of the true population. But so if you find the mean of this standard deviation data set, you will see that it is close, but it is not as close as we want. So the mean of the standard deviation data set is not close to the true standard deviation of our population. The reason because of this is that this is now how standard deviation works, but well, like you can't make a distribution and find the mean to find the standard deviation of the true population. But instead, if you just, instead of finding the mean for like if you, instead of finding the mean of it, if you divide it by the 1 minus the total number of samples, then you would get the standard deviation. So I will show you an image which will make it a bit clearer. Yep. Yeah, rather things. So instead of the standard deviation, so you make a distribution of the standard deviations, and the mean of the this distribution will not be close to the mean of the true population's standard deviation, but rather if you find the variance as, instead of, so in the mean we divide by the total number of samples, but in case of finding the standard deviation you have to divide by n minus 1, one less than the total number of samples, and that gives you very close to the true standard deviation of the population. So essentially what I'm saying is that instead of finding a mean, okay, here I can't do it. Yeah, so you have to change it in the formula itself while calculating the SD here. Instead of finding the SD using the function, you have to somehow introduce the n minus 1 here, and that will give you the true population standard mean. I will add the images here, which will make it clear later. Okay, we have now essentially found out the mean and the standard deviation of the entire population using just sampling. Everyone with me so far? So standard deviation এর জন্য instead of so original formulaটাতে we use n minus 1 times the entire variance termটা, but to find it from sampling you have to have this n minus 1 here, but the original formula has it as just n. So when you're sampling, if you just replace the n with the n minus 1, you divide with 1 less, then you get very close to the true population standard deviation.
Sir, এবার মার্গ বোঝাবেন?
আরেকবার বুঝাবো, হ্যাঁ। So first what we did is that we made the distribution of the standard deviation. So we found standard deviation from small samples and had it we made a distribution from that. This is my distribution of all the standard deviations of smaller and smaller samples. So now if I want to find out the mean of so if I want to find out the true population standard deviation from this distribution, what do I have to do? If I just do this, like I find the mean of all of this with the central limit theorem tells you is that the mean of the distribution, so I will write it down, it will be way easier this way. That mean of sampling distribution of mean tends towards population. So this we have already seen in the previous section, but the mean of standard deviation, the sampling distribution of standard deviation is not the population standard deviation. So if you make a distribution of the standard deviation of the entire samples that you have been taking, so that is not the standard deviation of the population. The mean tends towards the population mean, but the standard deviation of the distribution of standard deviations, if you take a mean of that doesn't tend towards the population standard deviation. Is that okay?
হ্যাঁ, বুঝতে পেরেছি।
Okay, everyone else also is fine with it?
Yes, sir.
Okay. So how do we fix this? We fix this by, instead of calculating the mean of the sampling distribution of the mean, so anywhere in the formulas for standard deviation you will find that this comes up all the time, that instead of dividing with n to find the mean, you actually divide by n minus 1. When you divide by n minus 1, you actually go closer to the population standard deviation. So here, instead of finding the mean, you actually look at like এই divide like mean করার সময় কি করবো, সবকটাকে অ্যাড করে সবকটার number of things I have been adding সেটা থেকে divide করে দেবো, but instead of that, so just give you an example. So if I do a sum of the SD of the distribution divided by total number of the distribution, that is 50 into 200, so it should give me the same result. No, it is not, but oh no, there is just 50 values, sorry, 50. So this is what the mean will give me, but instead if I do divide by 1 less, it will be even closer to the population mean. So essentially I'm saying that taking the sum, taking the final mean, divide by 1 less, and you will be able to figure it out, is essentially what I'm saying. So mean of the sampling distribution of mean equal to the population mean, mean of the standard mean of the sampling distribution of standard deviation is not equal to the population standard deviation. Essentially this is what I'm saying. But if you use n minus 1 during the standard deviation calculations, then you go even closer. Okay. Okay. So next, what we do is that we estimate something called the confidence interval of the entire population parameters. So what is confidence intervals? So say you are saying ki I have calculated from my sample I have calculated the population mean, but how confident are you that the mean is where you are saying it is? It probably is not exactly the sampling mean value that you have found out. It is somewhere close to it, but how close? That you refer to as being the confidence interval. The if you can find a small, like you found that yes, my sampling mean is 14.5, my sampling mean is like 99, and say you didn't know that the population mean is 100, you can say that I have a particular confidence that it is close to 99 but not exactly 99. So what is that range that you can give me that yes, mean will definitely lie between these two values? So this is known as the confidence interval. So if there is a 95% chance that the true mean lies between two different values that you can estimate, it is known as the confidence interval for the mean. So I am very confident, like 95% confident that the mean is between these two values, and that is how you use the confidence interval. Say if I say I am very confident that the true population mean will lie between 95 and 105, I'm 95.5% positive about that. That is what you know as the confidence interval for that distribution. And it is always the case for normal distributions, because we have drawn the sampling distribution of the mean is a normal distribution. We know that there is always a 95% chance that a normally distributed quantity will approximately fall within two standard deviations of the two mean. So anything you try and figure out, like it could be the mean of the entire sample, it will always be somehow between two standard deviations of the true mean of the entire population distribution. So yeah. So Q norm, this function we have looked at it the previous day. So we can find the different quantiles with this particular. So this we put in what the quantiles we want, and from that it will give me what the values of these quantiles are. So if I want to find the probability of the mean lying between 0.025 and 0.975, which is like 95% chance of the mean lying between these two values, and for the IQ distribution we know that 95% chance would be that the mean lies between 70.6 and 12.39. This means that there is a 95% chance for a normally distributed quantity to fall within 1.96 standard deviations of the true mean. So any kind of normally distributed quantity, if it is normally distributed, so it will always lie, the mean of it will lie within 1.96 standard deviations of the true mean, which mathematically we can write like this. So x bar being my uh, sample mean, and this guy is being my true mean, so it will always the sampling mean will lie within 2 standard deviations of the true mean. Okay.
Sir, can you repeat the thing one second? I missed the part. From Q norm, from the code.
Okay. So Q norm, when you write Q norm function like this, P equal to C 0.25 and 0.975. Essentially, you are saying what part of the distribution lies between 25, not even 25, 2.5% and 97.5%. What lies in between both of these? So essentially 95% of the entire distribution will lie in between these, and it gives you that this is the value of those numbers. So 95% of the entire population will lie between 70.6 and 102.39. So there is a 95% chance that the normally distributed quantity will fall within 1.96 standard deviations from the true mean. So 1.96, where did I come up with this value? So my standard deviation is 15. You just multiply 15 into 1.96. You will see it is 20.4. So it is 100 plus 25, 29.4, and 100 minus 29.4. So exactly what we got. So there's 95% chance. So essentially what I'm saying is that if we look at the normal distribution here, there is a 95% chance that the mean of the normal distribution will lie between 1.96 of multiplied by the SD on either side. So if I had two lines here, one going here, one going here, which mark the 1.96 SD point, so my mean is 95% probable to lie between these two limits. Essentially that is what the entire thing says. So if you write it mathematically, our true mean would lie 1.96 times the standard error of mean within plus or minus the sampling mean that we got. This is essentially what it tells you. And we know that the standard error of mean is sigma divided by root 2 n. So our confidence interval 95% is our sampling mean plus minus 1.96 into sigma divided by root of n. Is that fine?
Yes, sir. Thank you.
Okay. Okay. Next, we have seen that so this uses sigma, right? Sigma, if you remember, is the population standard deviation. Now, there is a problem. We just got to know that with the sampling distribution of the means, we can find out the population mean. But we cannot find out the population standard deviation, like, because it is always n minus 1, you have to divide it by, you can't estimate it properly. So how do you find this sigma? You are still lost here. This is one term that you can't estimate properly. You can, but you just don't have. The idea is that you won't use the normal distribution to estimate it. You will use the t distribution. You remember the t-test, guys, we were talking about? The t-tests, we had done one sample t-test, two sample t-tests, independent t-tests. So there is something known as the t distribution, which is much more narrower than the normal distribution. If you use that, then you can actually find out, estimate the standard deviation as well. Instead of the normal distribution, you use the t distribution. So if we use the t distribution, so like we have used the function q norm, qt gives you the t distribution for a particular value that you put in. So I'm saying I want to be as confident as, so if I put in c of 0.25 comma and degrees of freedom minus 1, oh no, not like this. Yeah, so you see that it is still between 1.96 of our standard deviation. So what we found out previously, here 1.96 we get from the t distribution. So essentially in this entire thing, we have been able to find out how to estimate the population mean from our samples. We can find the sample mean by figuring out the distribution of sampling distribution of the mean and finding the mean of that. We can find the population standard deviation by removing the systematic bias and dividing by n minus 1 in the actual formula for standard deviation and not n, and that way you can find the standard deviation from calculating the mean of the standard sampling distribution of standard deviation. And finally, confidence intervals, we always know that it will all the true mean will lie within 1.96 times the standard error of the mean, and you can find that out using this formulas. Confidence interval 95 is equal to the sampling mean that you have found out plus minus 1.96 times sigma divided by root of n. Okay, so does anyone have any questions from this? Okay, then if no one has any questions, that is all I had for today. I will just quickly take your attendance. Yes, so I think tomorrow we should be able to wrap up. So tomorrow there will be the final class for this entire course, and we will not have another exam. I don't think we have planned another exam, have we? Uh, yeah, we can have a final exam, but I was thinking that I can give you another. Hmm. Let me think about it. If I want a final exam for the entire course, or do I give you another assignment out that you will fill for the final grade?
Sir, assignment.
Sir, assignment is fine.
হ্যাঁ স্যার অ্যাসাইনমেন্টটা ভালো।
বুঝতে পারছি assignment is better, but I don't know. I will have to talk to RG and figure something out. I will let you know. I think they only said that it needs to be a final test. So let's see. Don't worry, অতটা difficult হবে না. Okay. Thank you everyone for joining. I will see you tomorrow, and tomorrow probably will be the last class. We will be covering RNA sequencing and how to analyze bulk RNA sequencing data. Okay, thank you everyone.
স্যার হ্যালো
হ্যাঁ হ্যাঁ
স্যার একটা কোয়েশ্চেন আছে, সেটা হচ্ছে যে আমার মাঝখানে কয়েকটা ক্লাস মিস গেছিল, তো আমার কিছু কিছু টপিকস বুঝতে অসুবিধা হচ্ছে। তো আমি এমনি কিছু ওই আরএমডি যে ফাইলগুলো আপনি আপলোড করেছেন মেলে,
হুম
সেগুলো একটু পড়ছিলাম, বাট আমার কিছু কিছু জায়গায় কিছু কিছু ডাউটস আছে। তো যদি মানে আপনার যদি টাইম হয়, আমি কোনো সময় আপনাকে জিজ্ঞেস করতে পারি?
হ্যাঁ হ্যাঁ ডেফিনেটলি ডেফিনেটলি তুমি আমাকে একটা মেইলে তুমি পাঠিয়ে দিতে পারো যে কি কি প্রবলেমস হচ্ছে, অ্যান্ড আই ক্যান লুক অ্যাট দোজ অ্যান্ড সেন্ড ইউ মেইল ব্যাক। আর যদি সেটাতে যদি না হয় তাহলে উই ক্যান হ্যাভ আনাদার গুগল মিট in which you can just ask me questions about things.
স্যার বলছি যে শুধু আরএমডি ফাইলগুলো পড়লে মানে একটু অসুবিধা হচ্ছে বুঝতে। আপনি কি কিছু অন্য কিছু সাজেস্ট করতে পারেন, মানে যেরকম পাইথনের নিজস্ব টিউটোরিয়াল হয়, মানে এমনি গুগলে পাওয়া যায়, এরকম আর এর কোনো টিউটোরিয়াল কোনো ওরকম ইয়ে আছে, ওয়েবসাইট আছে যেখানে আমি পড়ে পড়ে একটু আরো বেটার বুঝতে পারি?
What do you want to know? আর কোডিং এর ব্যাপারে বা স্ট্যাটিস্টিক্স এর ব্যাপারটাতে?
হ্যাঁ, কোডিং এন্ড স্ট্যাটিস্টিক্স দুটো ইউজিং আর।
ঠিক আছে, সো আই হ্যাভ বিন গিভিং দিস রেফারেন্স, আমার সবকটা ভিডিও ইউটিউবে আপলোড করা আছে, অল অফ দিস হ্যাভ দিস রেফারেন্স। ইট ইজ কল্ড Statistics with R, I think is the name of the book, by D Navarro. এটা online available আছে as a website, and you can just click on the link. I can even show it to you, I think. Statistics with R, D Navarro. Yeah, learning statistics with R, not this. There is an entire website which is free. Yes. Yeah, so learning statistics with R, you have introduction to R, data. Essentially, I have been following this particular book and so the course by Professor Arjun Ramkrishnan at IIT Kanpur to like make this course. So essentially, this book will follow the same things that we have covered. So you can just go ahead and look at it. There is an introduction to R, how to make vectors and stuff, and then t-test, ANOVA, Isha hypothesis testing, সবই আছে. So this I have given this reference in all of my videos as well. YouTube upload kora, but if you want it, it is just there. You can just go ahead and look at it.
ওকে স্যার, থ্যাংক ইউ স্যার। আরেকটা কোয়েশ্চেন ছিল
Hmm.
রিগার্ডিং, মানে it is not related to the course, but you are like doing a PhD in IIT Kanpur, right? So can I ask that on what topic are you doing your research?
On what topic I'm doing my research on? I am working on something called developmental biology. I am looking at how the brain develops. Like there is particular
Okay,
processes that occur during brain development, especially initially in the embryo. The brain is a single vesicle, so like a spear, but we know as vertebrate embryos develop they from the left and the right hemispheres. So I'm looking at that process particularly.
ওকে স্যার। স্যার এই পিএইচডিতে অ্যাপ্লিকেশনের জন্য, স্যার হ্যাঁ, পিএইচডিতে অ্যাপ্লিকেশনের জন্য কি মানে আপনি ডিরেক্ট গেট স্কোর দিয়ে গেছিলেন নাকি অন্য কোনো এক্সামস দিয়েছিলেন?
I went through gate. I went through gate. Yeah, I mean I have applied directly for PhD through gate only, বাট আই নো যে তুমি সিএসআইআর বা নেট এই এক্সামগুলো দিতে পারো। Just I think for both of these one of these exams you have to have a master's degree, but with GATE you can just apply after your BTech.
ওকে স্যার, থ্যাংক ইউ স্যার। স্যার আপনাকে আমি মেল করলেই অসুবিধা নেই তো, মানে যদি কোনো ডাউটস হয় রিগার্ডিং?
You can go ahead and mail me. Yes, definitely.
ওকে, থ্যাংক ইউ স্যার, থ্যাংক ইউ স্যার।
Okay. Then thank you everyone. I will see you next week.